Hey guys, welcome to the first video of our online teaching delivery. So today we're going to be looking at a topic, and it's on the area and perimeter actually of irregular shaped blocks of land. So in particular, what we're going to be looking at today is when we've got a shape that we can't traditionally find the area of, so it might be made up of not very nice shapes. What's one technique that we can use to actually find the area of one such shape? So our heading for today is, as I said, irregular or irregularly shaped areas. So in particular, the first thing that we're going to talk about is a rule, and this rule pops up in many different things, but it ties in quite nicely to area, and it is called the trapezoidal rule, like so. Now, the trapezoidal rule is essentially a rule where we make a bit of an assumption about a shape and we liken it to a trapezium. And so, for example, if we had a shape that looked a little bit like this, which kind of looks like we've got a bit of a rectangle with a semicircle on the end of it. But what we'll actually find is, if we separate this like so, what we've actually got here in our highlighted bit is a trapezium. And this is essentially what we're going to be working with. We're going to be making these regular shapes. We're going to find the area of them, and we're going to do so by approximating using a trapezium. So we'll start by jotting off a few notes. So some shapes are irregular. And this makes it difficult to find the area. And we'll add in and perimeter, because we're going to be looking at that a little bit too. And perimeter. So we can find the approximate area and perimeter by splitting these shapes into trapezia, we call them. And this involves using the trapezoidal rule. So essentially, we're going to take a shape, we're going to split it into some trapezoids, and we're going to use what we know about trapezoids to find either the area or the perimeter. Now, the general rule is that the more trapezia that we can fit into our shape, the more accurate it's going to be. So a common word that we like to use or that will pop up, and we've covered this earlier, is error. So essentially, this process that we're using isn't perfect, and there's going to be some sort of error. And we just need to be aware of that. The way that we minimize this area is we get more trapezia and we fit them into our shape. And what I mean with that is we'll look into it soon, specifically what I'm talking about. But we might start off with the actual formula that we're going to be using. And so the trapezoidal rule is area is approximated by h over 2 times by d subscript f plus d subscript L. And I'm just going to jot a little note off to the side where df is our first length, and dl is our last length. Now this formula here may look familiar, and it's because we've covered that earlier. We've used some different terminology in that before we weren't using df and dl, we were actually using, if you bear with me for just 1 second, we were using a plus b. And we also had the h at the end, but we're taking it out the front and we're just putting it on top of the 2, which we can do because we're dealing with division and multiplication. So this is the rule that we're going to be dealing with. Area is approximated by, so that's what this funny equal sign means, approximated, by h on 2 times df plus dl, where h is our height, df is length of the first side, dl is length of the last side. Now the height, I will just say, it isn't the traditional height in that sometimes we deal with up and down being the height. It actually depends on which way our shape is orientated. And what I mean by that is if we have a shape that looks like so, we're going to come across here and then we're going to have a bit of a curve here. So just assume that I've actually drawn a decent looking shape there. And then I'm going to draw that exact same shape, but it's just on its side this time, and I'll give that a little more curve there. If I were to turn these into 2 trapezia, I would split it down this way, and this one I would split it up this way. So even though we've got the same shape, it is different in how what I should be saying is our labels will stay the same no matter how our shape is rotated. So in this case, we would say that our h is here, and in this case, we would say that our h is down here. On our left side, df would be there. On the right case, df would be there. And of course, we're only left with dl, which would be here. Now, whichever one you deem to be your df and your dl, it doesn't really matter in this case. The main thing is that your height isn't on one of the sides that have the 2 different lengths. So if you can see here, one of these has to be df and one of these has to be dl because they're different lengths. If we called one h, we're just going to end up in a world of trouble. So just keep in the front of your mind that h has to be our one measurement, and later on we'll see it's the one that's consistent for each of our trapezia that we're drawing. Alright, so I had a bit of a technical difficulty. We're back on track now though. So for our worked example, I'm not going to pick one out of our usual textbook. I think I might come up with one myself. So let's get like a bit of a real life example happening here. So we're going to have something to do with a bit of a driveway. So we've got the following question. To calculate an approximate area for her driveway Zara took 2 measurements. Um, 5 meters apart, like so. So here's our diagram. So here's Zara's house. And Zara's house looks a little something like this. And we've got front door here. There's the house. And here's Zara's driveway. And Zara's driveway comes out like this. And let's say it goes a little something like this. Like so. So we got told that the first measurement across here was where Zara's first measurement was, and it was 8 meters. And Zara's second measurement was here, and it was 4.5 meters. And we also knew that these were 5 meters apart. Not to scale. Not to scale. All right. So essentially, the way that we're going to approach this question is, well, as we've been talking about, we need to turn it into a trapezium. And our trapezium is going to look like so. Now, I think for the sake of keeping this question doable, that's going to be a straight line. So that will make it a little bit easier for us. Okay, now our trapezium is going to go from this corner straight out. This is going to drive me absolutely nuts unless I fix it up. Let's put it like that. So now we actually have a trapezium. It's going to come across like so. And so I'm hoping that you can see our trapezium is this bit right here. Okay, so there's our trapezium. Now remember, our 8 and our 4.5 are our differing lengths. So even though they might not really look like it, they're going to be our DF and DL. So I'm just going to jot that down to the side. DF will be 8 and DL for last will be 4.5. And our height of our trapezium is going to be 5. And these are all in meters. So let's use our rule. Area is approximated by h over 2 outside of df plus dl, like so. We're going to sub in everything we know. It's 5 over 2 outside of 8 plus 4.5, which is 2.5 times by 8 plus 4.5 is 12.5. I'm going to pull out my calculator now. Obviously, you guys can't see this, so I'll just make calculator noises. Beep, 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 beep. And the answer is actually 31.25. Always important to remember what units we're dealing with. We're dealing with meters squared. Dealing with area. Okay. So Zara and her funky driveway, we could approximate it as having an area of 31.25 meters squared. Now, I'm going to have a look at a different example. And this example is one where we are breaking up our shape into several trapezia, as we were talking about before. And so it's going to be worked example, another one out of a different, or from a different source. So we've got worked example. And we will have the cross section of a river is shown. And we're going to use 3 applications of the trapezoidal rule to find the approximate area. All right, now this is where it becomes important. Well, I guess it's important in every case, but this is where we can really see how our H plays into multiple trapezia. So, we've got a fantastic diagram that looks a little bit like so. There we go. We've got, the question tells us that we've got 4 meters gap between each of these. 4 meters, 4 meters, 4 meters. This side here is 12 meters. This side here is 7 meters. And we've got 8 meters here. So let's say someone's gone along with some sort of measuring tape measure. Have to be quite a long one. They've swum to the bottom and they've worked out how deep this bit is. So I'll add some water. Because there's no point not having water in our pond. And because I know someone will be out there whinging about it, there's our fish. So here's our pond. If you can imagine, it's a cross section. So we've got some grass here, got some grass here. Nice little cross section of our pond. So it's as if we've cut it with a knife and we're looking at the side of it. So to find the area of the cross section, we have to break this down. So I'm going to call this one A1. We've got an A2 and we've got an A3. We're going to break it up and we're going to say that the total area is equal to A1 plus A2 plus A3. Same as when we were dealing with the composite shapes before. So the next issue that we have to come up with is, the next step of our problem is we actually have to turn these into trapezia. So this first bit, what we're actually going to do is, it might be easy to start off here at the middle. We're going to make this into a trapezium. Now it doesn't matter if it goes outside the lines, as long as this line is straight. Pretend that's straight. Oh my goodness, I've made it even worse. Let's fix this up. Oh no. Okay. Okay. So we're going to pretend that we've got 2 trapezia here. Now this trapezia is going to be a little bit funky, I'm not going to lie. What we've actually made is a triangle. Probably to lots of people's disgust. So we're going to break this down. We're going to find what A1, A2, A3 is. So area 1, this is approximately equal to H on 2 outside of D, F plus DL, just like our rule. Now off to the side, H is our constant length. It's the length that doesn't change in each So when we've got our differing sides. So in this case, it's going to be 4 meters. It will be this value, this value, this value. It's got to be the same when we're dealing with problems like this. It's going to be 4 meters. So let's sub that in, 4 over 2. Now, this point right here is going to be our first value. Now the depth right there at the edge is 0. Plus our last value will be 7 meters. Now, even though I started off by saying we've made a triangle, but we're using the trapezium formula, what I hope you can see here is that we've actually got a half of our height times by our base, kind of. So essentially, even though we've used the trapezium rule, or the trapezoidal rule rather, it actually has just broken down into a triangle. If that's nonsense, forget about it, doesn't matter. Just keep in mind you've got to sub into all these different values. So 4 over 2 is 2. 0 plus 7 is 7. So we're going to get an answer of 14 meters squared. Alright, now we go through and we do the next ones. A2, I'm going to speed through this because I think you guys will be getting sick of seeing this soon. Don't forget, if you're not sure about something, feel free to ask me, or you can also pause the video, have a look, make sure you understand it. Don't understand it, feel free to ask. So for A2, we're going to have 4 on 2, this bit's not going to change. Our first value is this bit right here, 7 plus 8. Our 8 comes from here, the depth right there. So it's going to be 4 over 2 is 2, 7 plus 8 is 15. 2 times 15 is 30 meters squared. Alright, lucky last. We'll use our same rule. H on 2, dF plus dL is approximately equal to 4 over 2. Our first value is 8. Our second value is 12. So we're going to get 4 on 2 is 2. 8 plus 12 is 20. 2 lots of 20 is 40 meters squared. Last thing we've got to do is, there's one answer, there's one answer, there's one answer. We've got to add them all up. So the total area, as our rule before, was A1 plus A2 plus A3. We're going to sub these in. 14 plus 30 plus 40 is 84 meters squared. All right. So those are just 2 worked examples of typical examples that we might use the trapezoidal rule for. Sometimes we may have to use the trapezoidal rule to find the area of some funky looking shapes. I think that just about will tie us up for now though. So make sure to give the questions a go that I leave for you in your Google Classroom. Any questions, you can email me, that's no problem. And any questions, email, or you can put them up on the Google Classroom. All right, thanks guys.